So let's start. Okay. Today I speak about optimization schemes in tensor network in the variational formulation of the tensor network state. Before that, I just announced that the paper for corner transfer matrix normalization group, there are two ones now free of access. Because I submit these articles to JPSJ, JPSJ, Japanese Journals of Physical Society. So for most of the foreigners, this paper was not accessible for long. That's why most of the case, CTMRG, the term CTMRG, they cite the paper of Roman Ols. Yeah, it is okay. It is okay. Their paper is quite good and comprehensive and self-contained. And here are just the originals. So what I will speak today is not fully new, rather than new, or it is quite old. So please do your homework if you prefer. Okay. So the theme of this lecture, or discussion, let us enjoy discussion, is this problem. How to obtain a good variational vector for a given transfer matrix. Of course, you can imagine quantum problems, because any kind of quantum problem can be formulated by means of classical transfer matrix. If you consider the correspondence between quantum Hamiltonian and classical transfer matrix. This is just a time evolution. And here is a reflection. Of course, you can construct a variational state by any means. For example, you can construct a variational state by means of restricted Boltzmann machine, or deep learning, or etc. And probably Tao will speak about Tao, not Lei, but you will speak about really. But unfortunately, I come here only Monday from now on because I have a lecture. Okay. So here is a restriction. The variational vector should be represented as matrix product state, or tensor product state, or equivalently projected entanglement state. Okay. Yes. Yeah. So there are many approaches. The most ancient approach is assume a local tensor, anyway, which contains a few number of adjustable parameters, and try to find out free energy minimum by adjusting this small number of parameters. This is the most naive usage of the variational construction of the variational state. And the more sophisticated one is treat all the tensor elements as adjustable parameters. So the difference between these two are the number of adjustable parameters. So in the scheme B, you consider each tensor element as adjustable parameters, and try to find out the variational minimum. Of course, this is our design. If we try to find out the maximal eigenstate of the transfer matrix, or Hamiltonian. And there are several approaches. Of course, if it is possible to search each parameter, each tensor elements, each by each, fully, And then it is apparent that one can find out a real minimum. Of course, there are many local minimums, but real minimums can be detected by the full parameter search. And this is very expensive. So I will keep this type of search for the next generation of supercomputer. This is very good for consuming CPU time. And the second one is stochastic search. So just set up a certain value for each tensor element using random number generator and evaluate the variational energy or variational free energy. And if the variational energy goes down, then choose that tensor candidate generated by stochastic numbers. And if the energy goes up, in that case, discard that candidate. By means of such stochastic search, actually it is very good. It works very good. And this was confirmed by Sandbeck et al. And here is the reference. It is very well, actually this stochastic search is very efficiently, but I haven't heard that people commonly use this type of search in our community. Of course, in the machine learning, they use such a stochastic search often, but for some reason, they do not prefer to use it. And B3 is the conjugated graded search. So just try to find a gradient, so decent direction of the free energy by changing the tensor elements bit by bit, each by each. This is a concrete manner of finding out local minimum. Of course, it goes down this gradient guide you to any local minimum. And I'm not sure whether you reach the real minimum or local minimum. So this is rather dangerous. And B4 is, okay, B3 and B4 are actually equivalently dangerous. B4 is deterministic optimization. And in the case of DMRG, DMRG cleverly avoid to reach the local minimum. Since, wait, I have to be careful. Actually, DMRG often goes to local minimum. It is confirmed. For example, let us consider a random bond one-dimensional Heisenberg chain. So if one considers the quantum Heisenberg chain, and if it contains any randomness, in that case, actually, the MRG calculation guides you to a long local minimum. From the energy viewpoint, actually, the MRG gives you a good variational energy. So the calculated energy by the MRG is as good as the exact energy. But when there is randomness, actually, there are so many numbers of low energy states where they have the same, almost the same energy. And actually, the MRG cannot catch this real local minimum. But this is different issue. Anyway, they are deterministic optimization. And in the deterministic optimization method, there are several classes actually. One is using, for example, one is using generalized eigenvalue problem to find out variational minimum. And the other is the time evolution scheme. And probably people are more often use this time evolution scheme. But anyway, there are so many schemes. And as an example of the type A, so A is to prepare some adjustable parameter and construct the variational state. The oldest, as long as I know, as I often present this paper in front of you, the oldest one is by Kuramas and Wani. And Kuramas-Wani, this is the paper in 1941, assumes that, okay, they consider the variational treatment of two-dimensional square lattice Ising model. So this is classical Ising model on square lattice. And what they did is to evaluate the variational free energy of the transfer matrix of the two-dimensional square lattice Ising model, assuming the variational state which contains only two parameters. And what they prepared for the variational state is just the Boltzmann weight for the one-dimensional Ising model and a certain external magnetic field. So in the disordered phase, this external magnetic field is zero, and in the ordered phase, the external magnetic field should be finite. Anyway, by means of this kind of simple variational state, which contains only two parameters. One parameter is external field, hypothetical external field, and the second one is effective coupling between sides. And if they find out, they detect the order disorder transition by this simple construction of the variational state. So here you see that the partition function lambda is then developed by using the matrix methods in variational form. I prefer this phrase. This is my Bible. Anyway, so I have spoken about the scheme A. Then what other examples can we find? Well, actually, the second might be B1, B2, B3, but actually B4 was established by Baxter in a very clever manner. So this is the now this is the well-known paper in this community probably. This is the paper by Baxter, dimers on a rectangular lattice. This is written in 1967. And looking at this abstract, so today, today, this lecture is not on physics, but on the literature. So let us enjoy reading their sentences. So looking at the abstract, Baxter says that a set of matrix equation is blah blah blah, and quite small dimension nullity, very good approximation to the thermodynamic properties are obtained. So Baxter already noticed that the only limited number of parameters should be used, and it is possible to store, obtain good variational free energy. Anyway, one has to read through the Baxter's article once. And surprisingly, Baxter wrote most of the important part of the dense network schemes in this article. But you have to bear his notation. Since there is no diagrams, there is no, Baxter do not use any tensor representation, but he uses used matrix equations. So you have to imagine the legs, tensor legs, looking at the renormalized equation, form of equations. Anyway, please open this paper. And later, in Baxter's textbook, this is also a good textbook, well-known textbook. Exactly solve the models in statistical mechanics. What he wrote is that density matrix of the trace of the multiple of corner transfer matrices. So around 1980, actually, tensor network formulation and assisted by corner transfer matrix was fully established. And in our community, Professor Okunishi, only he and Akutsu knows this fact. In those days. So here is discussion time. Anyway, as long as MPS is concerned, Baxter's method and DMRG, DMRG was established in 1992, sufficient enough. And but actually, here is point of one has to take care. These variational formulations normally assumes the symmetry in the transfer matrix. Of course, in the Baxter's textbook, if you open the Baxter's textbook, you find out that Baxter showed a way how to treat asymmetric transfer matrix. That's why he used different notation for A, B. Shows A and B are the variational state in the lower half. So A, B are kept, and C and D are Vula. And between A, B, and C, D, there is a transfer. And here is system number. So Baxter's construction is like that. And he wrote how to treat asymmetric matrix but here is a note that in order to follow the Baxter's way of treating asymmetric matrix, you need diagonalization of asymmetric matrix. And often one suffers from a tiny complex eigenvalue if you one try to use Baxter's method in numerical calculation. So one has to be careful. One has to take a special care to the treatment of the diagonalization of the asymmetric matrix. Okay. So normally it is not easy to treat a transfer matrix which is not symmetric. And here is first discussion time. What I would like to ask you is that whether your algorithm is gauge invariant or not. Well, what's the gauge invariance? So please consider a model defined by a transfer matrix T. And you can write down the same model by modifying a transfer matrix T prime. T prime is U inverse. So as long as you consider the whole system, because the whole system is constructed as the multiple of transfer matrices. So Z equals to Torres T and to M. So this is also Torres of U inverse to M. So you can multiply arbitrary unitary or arbitrary matrix, it should not be unitary, arbitrary matrix to your transfer matrix. And is your algorithm, numerical algorithm, is invariant to this type of case invariance. For example, suppose that you have a transfer matrix for Eisenhower. 2D Eisenhower. Please consider the 2D Eisenhower. And of course, it is easy to define transfer matrix T for this model. Then what's T prime? T prime can be obtained by imposing magnetic field H to each side, up direction to this side, and to this side, down direction. So it is the same as to multiply the term H minus H sigma I plus 1 plus sigma I plus 1 sigma I plus 2. And in this side, H sigma I plus 1 plus sigma I plus 1 sigma I plus 2. Okay. So just multiplying such a, just applying magnetic field to each side, so magnetic field of different side to each side. Then this kind of magnetic field cancels when you stack the transfer matrix. Do you understand me? Okay. Then I have a question. Is your treatment of tensor network formulation to obtain the variational vector invariant with this type of gauge transformation? Invariant? Do you believe that you're invariant? Okay. The point is that, for example, if you stack this kind of transfer matrix many times, so stack T prime, then what you obtain is a state, but most of the since there are fictitious field in this to the up direction in this side, so those states which have high spontaneous magnetization appears frequently, most frequently in this case, and in the same manner, Buddha state T prime. Of course, in this case, down. Equals what you obtain is a Buddha state, but in this case, most of the sides prefers to pointing downwards. So,
excuse me.
Yeah.
It seemed to be Ising interaction time, not magnetic field. Sigma and
Sorry, you're right. No. Sigma I plus sigma I plus 1 plus. Yeah, you're right. Sigma I plus sigma I plus 1 plus. Yeah, sorry. Thank you for pointing. Yeah, you're right. This is magnetic field. So, in this construction, a ket vector if you construct the ket vector, then what you detect is the state where most of the sides pointing to upward appears most frequently. And constructing the plus state, then you obtain the distribution, Boltzmann distribution, where most of the sides are prepared to point downward. So since these are the Boltzmann distribution obtained by such transfer matrix, as long as so Bra and Ket are totally different states. Of course, if you multiply these two, then this effect cancels out, and you obtain the original situation or original model. But as long as you define, you try to find out construct NPS in this manner, then actually important part of the very important part of the wave function and Bra state and Ket state are lost when you restrict the number of degrees of freedom by transforming this state to matrix product state. So actually this is a big problem in the formulation of matrix product state. So you need some pre-process for the obtain a given transfer matrix. And there should be some optimal pre-process for this kind of asymmetry, this kind of transfer matrix which is not symmetric. You might expect that I have an answer, but actually I do not have answer here. So I just present you that there is such a problem in the formulation of test network state applied to statistical models. Do you have any suggestion for that? No? Tomorrow you will speak about operational states.
Yeah, we have the same problem.
You have the same problem. Okay. So everyone shares the same problem. Okay. So let us end the discussion time and okay. So TDD actually anyway TEDD scheme does not work when H time is so strong. Okay, go on to the next one.
How much?
Yeah.
You can treat this as a symmetric transfer matrix, and choose if you define the density matrix in a non-symmetrical way, then this is part of pencil.
So now you are imagining the TMRG, transfer matrix imagine.
That's right.
Okay, let me see. So what you recommend is to use the by orthogonal MDS.
Not this.
Uh-huh.
But then also there are other ways.
Okay. So, okay. I agree with you. So in that case, you have to use diagonalization of asymmetric matrix.
That's right. Yeah.
Mm-hmm.
This is actually the problem matter in the quantum transfer matrix.
Mm-hmm.
Because quantum transfer matrix is not symmetric.
Okay. In most of the cases, quantum transfer matrix is asymmetric. But actually, it is asymmetric, but when you reverse the time direction and also reverse the space direction, actually you obtain the same state.
Anyway, but in that case, the transfer matrix itself is non-symmetric.
Okay, I agree with that point. Okay, so that way of treating this system is an answer to this question. Yeah. Okay. So what I learned now here is to focus on Tao's original paper. I will include. Okay, so then we go on to the next one. So I have shown that the okay, B4 is known by Baxter. Then there is no need to speak about B1 or B2, B3 or any approaches B. But Baxter shows that what Baxter has shown is the approaches for two-dimensional classical system. And so anyway, one has to consider some other way for higher dimensional system. So let's move on to three-dimensional eigenvector. In that case, one has to consider return back. So for three-dimensional classical eigenvector model, one has to return back to the position A, because so from now on, what I will speak about is our approach. Our means that Okunishi and me. Actually, Okunishi, who is very busy and cannot come here so frequently, but he will appear here on 5th August, probably. Anyway, what I will speak here from now is our approach to the three-dimensional algebra model. So one is this approach, A. Assume a local tensor which contains few numbers or parameters. Actually, this is Cramer's one-year approximation. And if you access the older paper, what you might find out what we did. So what we did in the ancient paper, it is already 20 years ago. You might think that 20 years is so ancient, but actually 20 years passed very rapidly upon you. Anyway, what we wrote in this paper, this paper is now free on access. We prepare two-parameter bracket weight B and construct Boltzmann weight. So what we prepare is a very simple weight. A W equals 1. Equals to E minus K plus K. What we assume in this article is a bracket weight. So this is different, so different from the tensor network state. But it is a direct extension of Cramer's one-year approximation. And it contains two parameters, K and L. And actually, this approximation was very successfully applied to the three-dimensional algebra model, and obtained transition temperature was as precise as different from the true transition temperature detected by Monte Carlo by 1%. Of course, 1% difference is very large from the sense, in the sense of Monte Carlo simulation, but it was, I was surprised that 1% precision of 1% was achieved just by using this kind of simple local weight. So, so just aligning this simple local weight, you set up a variational scheme. So the denominator is the norm of the variational state, and numerator is B multiplied T trans matrix and take inner product with T, and you obtain variational energy. And of course, when you try to obtain numerator and denominator, you have to treat two-dimensional classical lattice system. And both of the numerator and denominator was calculated by CTMRG. So it was an application of CTMRG to three-dimensional system. So anyway, in this manner, for three-dimensional Ising model, it is possible to apply a variational scheme.
Yeah, I had probably a naive question. Since here there's a data symmetry, why in the variational cat orthogonal rate you need this character which brings the data?
Okay. So you are right that the transfer matrix has G2 symmetry, but in the low temperature side, this transfer matrix has two maximal state. One is polarized to up direction, and the other is down direction. So as Tao said, that there is the symmetry breaking. So in order to express the symmetry breaking, you have to put L magnetic field to the variational state. Okay.
The symmetry of the transfer matrix is different from the symmetry of the unit. Because having infinite system.
Yes. So yes, infinite system. Or even finite system, if there is, if those two states, which is polarized to downward and upwards, are so separated, in that case, numerically speaking, they are totally decoupled. So it happens. Probably it happens in machine learning, If there are two states very far apart, then you can't reach from one to the other.
Question. Suppose you apply this kind of variational wave function for three-dimensional transform matrix. Then at the phase function point of this approximation, what's the value of K and L?
Okay. K changes continuously, and I forgot the right value of K, but K is always close to original K of the band part. Yeah. But K has some kink, not similarity, but K has kink at the criticality. No, at the transition point. Okay. And
Approximate transition point.
Approximate transition point. And L, speak about L. L is 0 in the disordered phase, and L is appears to be finite.
It's just like a mean field.
Yes. Actually, the transition class is mean field. And at the transition point, this is important. At the transition point, the correlation length of this variational state is finite.
I see.
Yeah. Thank you for that. That is an important point. And actually, we encountered the same situation for the application of a tensor product state to the transfer matrix. I haven't heard that one okay. Quite recently, there is a paper that they succeeded to obtain very long correlation lengths at the transition point by using very precise variational tensor product state which contains many degrees of T.
So one more question.
Yeah.
In this original paper, how did you optimize those two parameters? It's like two parameters.
Since there are only two parameters, we just sweep these parameters by hand.
Okay.
Yeah. Okay, here is an important part, and in particular to students. Okay, such a two-parameter search. For example, we set up K and L once, and change the value of K, and then you compare to, then you can do binary search. So actually, only 10 trials or 20 trials, you get the right answer, right variational minimum. But if I ask the task to the student, they tend to change K and L just by 0.01, 0.01, and repeat the million times of calculation to detect the local minimum. So this is what students tend to do. But actually, it is very rapid to obtain such a local minimum by hand. Okay. So this is original. And the drawback of the crowd mass value approximation is that you have to set up the form of local variational state by hand. So in the second trial, as a second trial, this is published in 0001, submitted 0001, and what we did in the next is to, okay, anyway, let us keep the form of variational state, variational construction of the local state. But since there are 16 parameters, so sigma, sigma dash, those four spins points upwards to or downwards. So there are 16 parameters. So treat these 16 parameters as parameters and try to find out variational minimum. So it is possible, since there are only 16 parameters, it was possible to do full parameter search. But what we did is, what we tried is the graded search. So B is the variational state, and which contains 16 parameters. So change one parameter and try to detect the change in the variational variational lambda. This is okay. Everyone, okay. This variation can be represented as the sum of variations that comes locally from each variations of the local local tensors, local weights, not tensor in this case. Anyway, it was easy to adjust and adjust the tensor element. But what we did is to do the optimization of the tensors in a self-consistent manner. And wait, but in this article, okay, let's see inside, some inside. This type of figure appears. Okay. So this is 0001, and we considered two types of construction of the variational state in this article. So as an extension. So what's this? The top, what you see is the placket. So that's the placket. So in order to increase the number of parameters, you can put auxiliary variables and form such a tensor. Or the other way is to prepare this kind of four-leg tensor. We just wrote the possibility. That's just possibility of using this kind of construction. But please read this part. We consider the simplest example A-type product state in this article, and actually, what we treated in this article is that the state number of this auxiliary variable is only 1. It means that there is no auxiliary variable. So in this article, we only treat the same type of variational state in as the Kramers-Mania approximation. Anyway, we consider this type of variational treatment as the generalization of DMRG to higher dimension. So actually, we prepared this type of tensors as the generalization of variational scheme of DMRG. And we consider two types. And what you find is that, please look at that. Figure 1b. This construction is not our original idea. Actually, it was written in reference 15 and 16. What's that? One is 15 in 1997, Enigma and Krupa Chitters, which was appeared in Nuclear Physics B. And the other is Okunishi and Hieda, Akutsu, New Zealand Physics. So anyway, around this year, already this kind of construction was used in a very special, only a very limited case, but it exists. And okay, so anyway, it was possible to obtain the variational minimum. And if you go looking into this article, you find out, okay, these are just variational treatment, and finally, what you reach is this equation. This is generalized eigenvalue equation. Of course, as long as you assume such a construction where the variational state is represented as the product of local tensors, if one try to maximize the variational partition function, every time you encounter this kind of generalized eigenvalue problem. And actually, this equation is rather difficult to solve. So sometimes this equation is ill-conditioned. Ill-conditions means that the singular value or eigenvalue of the matrix A, or the matrix which is written here becomes very singular. So it is always difficult to solve this kind of generalized eigenvalue problem. This is a reason why people do not try to use this approach, generalized eigenvalue problem, so often. They prefer, more often they prefer time evolution scheme. This guides you to the variational minimum automatically. But real minima can be detected by the linear this kind of generalized eigenvalue problem. Okay. So anyway, we have achieved the way to optimize a variational minimum automatically by means of a kind of gradient method. So probably the next approach, let us move on to the next article. The next article might be the establishment of tensor product state applied to three-dimensional eigenmodel. So in this article, which was published in 1901, 2001, what we considered is the vertex representation of the transfer matrix of three-dimensional eigenmodel. three-dimensionalizing model. Before, in the previous approaches, like this one or Kramers-Vanni approximation, this one, Kramers-Vanni approximation, we use this kind of IRF representation of the transfer matrix. But from this paper, we try to use vertex representation of the three-dimensional azimuth. And actually, in the field of statistical mechanics, the term vertex and IRF was widely used. IRF in the round phase. IRF. So interaction around the phase is the mode. So it means that if you consider square lattice azimuth model, then you can put Boltzmann weight to each placket, and each placket interacts with other plackets through faces side. So in interaction around the phase, IRF is often used in the field of two-dimensional statistical mechanics. And vertex is vertex, or in one notation, probably it is easy to represent it as tensors, Tollett tensors. A vertex is a vertex, and you can define any two-dimensional system as it's confusing. So two-dimensional azimuth can be represented as the stack of vertices, and these two can be mapped with each other. This is vertex IRF mapping. So this keyword, vertex IRF or IRF vertex mapping or transformation, was widely used from the ancient time. And so people who are treating statistical mechanical system equally consider these two expressions. For example, surface models. So if you consider the surface, crystal surface, in that case, IRF representation might be better. For example, solid-on-solid model can be presented by IRF model, and it is easier to use IRF rather than vertex. But anyway,
Is this some kind of duality transformation?
yes, that's it. Duality. Yeah, duality is important. Yes. So, for example, a loop and pots. That's a duality, and that is a kind of this example. So anyway, we used vertex representation and constructed the variational state by means of tensor product state. And probably the tensor product state, the term tensor product state appears around here. And it contains 2 chi to 4 parameters. So in the case of chi equals 2, it has 32 variational parameters. Yeah, 32. And those 32 parameters can be optimized by means of self-consistent improvement. Yeah. Anyway, this is just variational optimization. And such a variational optimization guide you to the right variational minimum. This is the spontaneous magnetization calculated by chi equals 2 tensor product state, and the real line shows the magnetization with respect to temperature calculated by Monte Carlo simulation. So actually, it agrees with very good. And in those days, actually, to tell the truth, in those days, in this article, no, in the previous article, in this article I have discussed, we were not, Okumichi and me and Andre Vendia was not able to optimize the tensor in the case where chi is larger than 3 because of the numerical instabilities. And this instability was recovered when 2 years later by means of stabilized manner of improving the local tensor. So probably it might be good to move on the next discussion time.
Excuse me?
Yeah.
Before that, for the instability, do you mean the instability in the generalized eigensolver?
Okay. A generalized eigensolver works, but actually, sometimes this gradient, so we use a kind of gradient search, and the gradient search, this gradient search tend to shrink the norm of the denominator of the variational formulation, and this is nothing because variational state, the norm of variational state is just a norm. So the point is, we were not able to find, how to say, optimize the parameters in the right manner. So it was numerical. So okay. So in the succeeding improvements, we prevent this change of local tensor. So we fix the norm of the local tensor to prevent the change of local tensor to the direction which changes the norm of the variational state.
I see. Because in the objective function, the normalization doesn't matter. But if you just apply gradient, I mean, it might change the norm. You have to project away with the component change the norm.
Yeah.
So when you do the variation, you should have a constraint, right? When you do the variation, you should have a constraint.
Yeah, constraint that the variational norm of the variational state should not be changed. Okay, so let's move on to this discussion time. And actually, I already forgot what I written in this page. Since time evolution scheme works efficiently for most of the case, the usage of generalized eigenvalue problem, which is often unstable, has been forgotten. Okay, this is current situation probably. Right? Forgotten? Okay. And even the gradient search and stochastic search are really used. And well, in the time evolution scheme is that stacking the tensor transfer matrix many times to improve the variational state. I love the full update. Okay, so in the time evolution approach, there are simple update and full update. And people says that they are just the difference of the complexity, numerical complexity. But actually, in my viewpoint, you might disagree, but in my viewpoint, simple update violates or worsens the right TPS. Right TPS, what's the right TPS? Right tensor product state is the fully maximized, fully optimized tensor network state, which gives the local minimum. So suppose that here you have tensor network state which is really fully optimized, and apply the tensor matrix, transfer matrix, and try to optimize it. But since this original tensor product state is already optimal, so there should not be any change. And if you use full update, there is no change. But if you apply simple update, actually there is a change. There is a change means that simple update violates the true fully optimized tensor network state. Does anyone object to me?
I think your statement is correct only when we assume that you can compute the correct environment for the given tensor.
Yeah, okay, of course, yeah.
But usually we use approximation in doing that.
Mm-hmm.
Yeah, in that sense, even if you use the so-called full update, still, you can move away from the real optimum.
Yeah. So in the case that you get fully reliable sense, always you have to exclude the term exact, because there is no exactness in your field. But agree only if you get agreeable environment. In that case, do you agree this statement?
Yes.
Yeah.
Are you talking about transition environments?
Yeah, wait a minute. This is not dependent on translational invariance.
Yeah, but generalized eigenvalue problem.
Okay.
What do you mean then?
Generalized. Wait a minute. Generalized eigenvalue problem. Okay. When you use generalized eigenvalue problem, the system should be translational invariant to the time direction. And to the two-space direction, the system should not be translational invariant. Right?
Yeah. Otherwise, the cross function is not linear.
Yeah. So for the case where there is a full randomness in three-dimensional classical system, like plus minus J Ising model on three-dimensional lattice, in that case, the only way you can apply is the time evolution scheme or Statkin scheme.
I have a common question is sympathy and approach. Sympathy is where they like to take infinity dimensional expansion. That's an infinity approximation, infinity dimension approximation, something like that. So this is very like the MFT. So you take infinity approximation, and then you want to improve it, then you make a cluster MFT. Okay? So if you want to do this very quickly, you can increase the size of the cluster. Then eventually you will reach roughly the same result as Forkit. If you can do this very large cluster.
So if the correlation length is sufficiently smaller than the size of the cluster, I agree with you. So near the transition point, still there is some danger.
Right, this is like a mean field approximation.
That's the point. That's a good point. As long as we use tensor product state of finite chi, at the very vicinity of the transition point, we obtain the mean field behavior about the phase transition. That is confirmed by Baxter-Tan anciently, and recently confirmed by Anderson et al. And actually, for the simple update, it is difficult to point that mean field behavior. Have you ever observed a transition by transition behavior by simple update.
Yes.
Was that mean field like?
We didn't check that whether it's Newfield like, but people say it's very likely to be Newfield like. We didn't really check that exponent very carefully.
Okay, okay. So what I spoke here, for example, what I have seen is that they, for example, they apply sometimes, I don't say who, but sometimes simple update scheme is applied to the phase transition of two-dimensional transverse field Ising model. And I often met the people that this is the temperature, this is magnetization, and their magnetization becomes this is the actually this should be and this is the result by full update. And this is by simple update. But then, as long as I have seen on articles, when they use simple update, they have such funny behavior. And when they use full update, they really obtain right answer.
I think it depends on how you do this synoptic. My experience. We didn't say that consensus, we say always at the bottom.
Really?
So you do this synoptic very quickly, each step, and you get that.
Yeah.
If you do not do it very carefully, you get it.
Yeah, so anyway, so if you encounter this kind of funny behavior, please check your code. So thank you for the comment.
So you mean you always get the new field behavior, no matter how large the D you use?
Yes. Actually, it is quite difficult or quite rare. I say that quite rare that your tensor product state gives infinitely long correlation length because this kind of variational state, this kind of variational state is two-dimensional. Two-dimensional means that as long as this chi is finite, this is just a two-dimensional one. So every criticality should be the criticality of two-dimensional classical system. And even when these tensors are fully optimized, it is quite rare that the correlation length of the variational state is infinite. So always the correlation length is finite at the transition temperature. Does anyone encounter the case where the correlation length is of your tensor product state depth is infinite at criticality?
Shunyoni is going to talk about something related to that tomorrow afternoon.
Really? Tomorrow afternoon? I would like to hear, but I'm not sure whether I can be here or not. Okay, tomorrow. I don't know. Tomorrow afternoon I have a lecture.
Oh, the day after probably. Tomorrow afternoon you have a lecture back in Kobe.
Yeah.
Oh, I see.
Yeah. Anyway. Okay. So your correlation length is always finite. Does anyone encounter the? So you tomorrow afternoon. Please come here tomorrow afternoon. I might see the video afterward. So, wait. I forgot to say something. I forgot to say something. Okay. So, back to this approximation, tensor product approximation. I said that I use the self-consistent optimization, but I was not sure whether that self-consistent optimization is properly performed. So actually, I did full parameter search. So there are 32 parameters. So I did full parameter search, and I also did conjugate gradient search. So I did several kind of approaches and confirmed that the self-consistent approach gives the right answer. And here, I ask you a question. So they prefer to use the stacking picture. And the stacking picture, if you use stacking picture to the tensor, so suppose that you have a tensor chi, and stack a vertex. So this is tensor, local tensor. A, sigma, eta, and this is W. Wait. Then you obtain. So here you have tensor and stack W. Then you obtain a new tensor. And the new tensor has a, since this is D, so probably you get the new tensor B sigma A dash U dash, and these are chi-state, and these are chi-D state. Chi-D state. So the tensor B is improved by stacking the weight, but the dimension increases. So you have to perform some kind of RG transformation, RG, to decrease the dimension of B to A. And my question is whether this kind of RG transformation from the extended tensor to original tensor, tensor of original dimension, can be done by unitary matrix or not. Unitary matrix. So this is B, and just applying some unitary matrix. So probably use some unitary matrix, which is pitch. Pitch is pitch, and pitch is pitch, and that is pitch. Okay, so these are unitary matrix. U is chi and D and chi. So RG transformation is performed. Do you believe that there is a unitary matrix which guides you to the right variational minimum, repeating this stacking? So suppose that you have some unitary or orthogonal matrix, and there should be a right unitary matrix. There should be. And using this unitary matrix, just prepare some initial tensor. Initial tensor can be arbitrary. You can arbitrarily choose an initial tensor. Initial tensor and stack W on top of the tensor and apply the unitary. And always, let us always fix the unitary. Let us always fix the unitary. And apply and stack again and apply unitary transformation and stack again.
This is roughly equivalent to simplicity.
Okay. In the case of simpler plate, you create this unitary from the singular value composition of the tensor, stacked tensor.
I mean, it's roughly equivalent.
Roughly.
Not exactly.
Okay. So my claim is that there should be there should be a class of unitary transformation which guides you to the right local minimum.
Actually, we did that before because this is just you can get your fixed point equation.
Yeah.
Because every time you get converge, the unit should be also converge. Right? So you can solve a local equation to get this local.
Local equation.
It's a fixed point equation.
Yeah, is that the right fixed point?
It's the fixed point if you do this kind of things approximation many times, then eventually will converge.
Converges. And my question is that, okay, suppose that you fix U by some means, you get to the fixed point. The fixed point specified by U.
Not fixed U. The fixed points, then U will also become fixed. Up to a KT transformation.
In what manner U is fixed?
No, it's not fixed. I mean, just you're going to converge U.
Converge.
Never give you a fixed point equation. You can derive your equation for this U. Now, solving equation, you can find this. Anyway, this is my. We did that. We didn't publish anything, but that's something.
No, but please publish it.
Because I think the result is not. Very likely the result obtained from a sim object.
Okay.
So that's why we can.
I recommend people to publish your technique if you don't have, because what I have experienced or I have seen in this field is that everyone is repeating the same technique on and on and publishing papers on and on. So actually each of you have a very skillful techniques, but that was not published. Publish it, please.
Right, okay. So we did this quite a long time ago, so I remember that.
Okay. Then would you agree that there should be a right tensor which guide you to the real variational minimum specified by given chi? Then the next question: how to find out this right unitary tensor?
I can tell you, but I forgot about the details.
Yeah, actually, to find out this unitary is far easier than to find out real minimum, because this is chi d, so there are chi for d parameters. But in this case, there are two chi 2d parameters. Yeah. So just by suppose, even in the case you perform the full parameter search, actually the search for U is far easier than search for the tensor. Yeah. Even for the case of stochastic search or gradient search, the search for U is far easier than search for this tensor. So please check, try. Actually, I confirmed it for the case of 3D Ising model, and in the case chi equals to 2.
I have another comment. Actually, in the early years, the fourth date is done this way. The fourth date is done this way. In the early years.
Early years?
Yeah, because for example, in Cobble's calculation, Philip Cobble's,
Philip
when he
Cobble's.
do the fourth date, that's what he did before. Is to update this bound unitary matrix.
And the
Actually, most of the people, when they do the fourth date before, then they do this way. They just calculate this U matrix rather than this tangent itself. So it's not just really a computer new thing. I should mention it. But of course, for the
okay. Yeah, I agree with you. And so when you do the full update, but the full update is very valuable, time consuming. So in the case of you use the full update, you probably reach to the right.
yeah, but I mean there are two kinds of update. One is for update the update of tensor itself. Another is to update the bound or transfer matrix, the bound unitary matrix.
How it is improved?
This is like a cut like you cut a bound. Say you can calculate the bound density matrix.
And bond density matrix, that doesn't give you guidance to the right one.
No, that doesn't mean that you need to do that way. I mean, it's similar as in BMRG. BMRG is to cut the bound, right?
Yeah.
That's similar. I mean, the similar, not
Similar.
You can minimize this U matrix or minimize the tensor itself.
Yeah.
So
I see.
of course, minimize the tensor cost is more expensive, the cost is higher, and it's also actually vibrate.
Yeah.
But if you just minimize this bound matrix, then the cost is lower. So depends on what you choose.
Yeah, so what I would like to say is that since nowadays we have a supercomputer, and it is easy to create the candidates, like variational candidates of U. So U is just a unitary, so there are only wait a minute, chi square divided by 2 direction, or roughly equals to chi square. Roughly preparing chi square, chi square directions, modifications of U, and just distribute it to your processors to calculate the variational energy. You obtain the gradient, and gradient you can do gradient search for U easily. So this is easier, far easier. I mean, this is far easier than creating the environment in full update. Since what should be done is just to prepare U and repeat it, and to find out the fixed point for each U and obtain the variational lambda. And the variational, each time you fix the U, you obtain the variational lambda. So the gradient search for variational U is easier, very easier.
So let me try to understand it. So are you suggesting that instead of, because in the original formulation, I had my boundary path, right? Sandwich. There's a sandwich. I put my transfer matrix in the center. Then that's a variational calculation for the state. So here you are suggesting that let's parameterize a family of unitary those kind of U matrices, and I need to then use that to find a fixed point of those boundary paths.
Yes.
Then I calculate the expected value.
Yeah, expected value for each specified U, and try to find out the optimal U that gives the right answer.
So then there will be some additional calculation for the projection, because I need to do this projection many times to reach the fixed point.
Yeah, yes. Of course, it is possible to accelerate. There is a way to accelerate this stacking process.
This fixed point.
Yeah. Okay. So, are you satisfied? Okay. I'm not sure.
Sorry. Then I can imagine that in this way, the variational space for those states are limited, right?
Limited, yeah.
Because you are doing the search in a smaller space
Yeah.
compared to the original.
Mhm.
What justifies this limit constraint for the limited search space?
Mhm.
That is something I do not understand.
Mhm.
Because here, the variational space for my state is going to be a fixed point of this kind of projection.
Yes.
Right.
Mhm.
And I try to convince myself that doing the variational calculation in this constrained space is the right way to do, because I still do not get. Maybe this is related to the question here. You
Yes.
put in the right picture.
Yeah.
But at the moment, I'm not.
Yeah, as long as you fix the number chi, your search space is limited.
I mean, you can still tune this.
Yeah. Of course, if you change chi automatically or dynamically, in that case, that's the different issue. I just fix the chi to a certain number and consider that space. Okay. And the rest of the time, I might speak about improvement scheme that I have. That is quite similar to IDMRG. In the series of tensor network workshop here, I probably have not speak about this approach, product wave function renormalization group, which is quite close to the IDMRG. So this is kind of accelerated infinite system DMRG. Yeah. So in this article, what is written? So back to 1996, I considered a variational wave function which is expressed as a matrix product and which is improved through a self-consistent calculation. And actually, this is a kind of CTMRG applied to quantum system, quantum counterpart of CTMRG. And this approach, product wave function renormalization group, PWFRG, gradually reaches to infinite uniform MPS as the case of infinite system DMRG applied to two-dimensional Argin model. And in DMRG, normally they use the diagonalization of renormalized transfer matrix, super transfer matrix over Hamiltonian. But in the PWFRG approach, no diagonalization is required. And this is common to CTMRG. And okay. So what we did in this was okay. So in this article we used IRF representation, but it is rather difficult to see the IRF representation. I used the vertex representation in the explanation of this approach. So let us consider two-dimensional Argin model represented as vertex model, vertex model. Then the transfer matrix is like that. So every circle means local vertices, and the transfer matrix of the system is constructed, is represented as this. we suppose that there you put some boundary condition to the left and right border. And applying the MRG to this kind of transfer matrix, what you consider is the renormalized transfer matrix. Renormalized transfer matrix consists of 4 parts. This is a left tensor, and in the middle there are 2 vertices, and in the right you have new tensor. You have another 3-leg tensor. And transfer matrix is represented, renormalized transfer matrix is represented in this manner. So this kind of picture you often encounter in the paper of DMRG. And in normal DMRG, they diagonalize this renormalized transfer matrix and obtain the maximal state for the corresponds to this renormalized transfer matrix, and using that and performing the singular value decomposition, you obtain the renormalization group transformation U to extend the system. So this is very well known DMRG algorithm. So and in the middle there is singular value or eigenvalue of the eigenvalue of singular value. Here is the singular value. And one point I would like to point out is that if infinite system DMRG applied to 2-dimensional Ising model is quite close to ITBD. Because stacking the renormalization group, renormalized transfer matrix in the vertical direction, this is just a tensor network. And if you find out the transfer matrix, here is the transfer matrix. Yeah. And left side and right side, what you obtain is the matrix product state. So there is right matrix product state and transfer matrix, and left matrix product state. And everything is uniform to the vertical direction. So this is quite like ITEBD. So actually, what White did in his first paper appeared in PRL. That was actually ITEBD to time direction. And yeah, so there is a hidden relation between TBD and infinite system DMRG. Anyway, in DMRG, one has to diagonalize the transfer matrix. But actually, okay, and I have to explain why this kind of transfer matrix diagonalization is necessary. In the DMRG, you have to wait. In the DMRG, what you did is to find out the eigenstate and performing SVD to obtain normal orthogonal matrix used for RG transformation, and the important step is the next. In order to extend the system size, so as long as you fix the system size, every system size is fixed. But in the infinite system DMRG, you have to extend the system size. In order to do that, you perform RG transformations. So, okay, this is actually the stacking scheme. So, you prepare 3-leg tensor and put tensor here, local tensor here. And then you obtain extended tensor, and by applying the unitaries, you obtain renormalized or improved local tensor. So this improvement is the same as what I spoke here, actually. So Actually, infinite system DMRG is nicely designed stacking scheme I have explained in this whiteboard. And in this case, in the case of infinite system DMRG, what applied to two-dimensional classical system, this algorithm automatically guides you to the right choice of U, and as an effect, you reach the right choice of a fully improved local tensor. So, in the case of 2D classical system, this assumption is actually correct. But I'm not sure whether it works in 3 dimension or not. But anyway, you obtain the renormalized or improved local tensor. And using this improved local tensor, you can extend the size of the transfer matrix just by putting new weight in the middle. So in this manner, you can gradually improve the right and left matrix product state in infinite DMRG. And so infinite system DMRG is very stable and reliable algorithm from the viewpoint of this kind of stacking process. And the only point is that the only point which is very numerically expensive is that you need diagonalization, not just diagonalization of the local tensor. That's very expensive. So what we did, and actually it is also done in IDMRG, is to skip the diagonalization scheme somehow. In the case of IDMRG, they construct, Ian Macro construct a candidate of variational state by combining original tensors and similar values. But here, we did it in different manner. So these are contents we have. The first, originally we have some sort of variational state written as a product of similar value and orthogonal matrices. And what is this? After stacking renormalized transfer matrix, you obtain some state, and performing singular value decomposition, you obtain improved transformation. Yeah. And what we need is some matrix which is which should be applied to this improved or extended transfer matrix that consists of improved tensor and local tensors. So this part is missing. So this part is missing, but we have these two, original one and improved one, and we do not have the right candidate of the variational state for the extended system. So what we did is just to do this kind of transformation. This is, so originally you have the orthogonal matrix, and applying the improved unitaries, you obtain new orthogonal matrix. So in this manner, you can create a variational state for the extended system. And in the thermodynamic limit, since at the fixed point, this transformation do nothing because two unitaries becomes identity, so this becomes identity. Yeah. So this is our approach, which was done in 1995. And actually, it gives you the correct answer very rapidly. And later in 05, we reformulate or we rewrite the whole structure of the tensor network state in terms whole structure of product wave function renormalization group scheme in terms of matrix product formulations. And later in this article, we present the classical background of this scheme. And actually, this is the same as a corner transfer matrix renormalization group. Anyway, what I have spoken is the improvement scheme, stacking scheme. And stacking scheme works in the case of 2 dimension. And in 3 dimension, sometimes work have not checked fully. So here is a discussion. What is the 2D or 3D generalization of PWRG? I have no answer yet. So we have passed through the variational schemes. So we have seen this, and as long as I see, actually, every time, so as you know, every day I check archive articles, but for these 3 days, I cannot update it. So today, after I return back to Kobe, I update it. But every time I encounter each paper, articles on tensor network formulation, they are rely on either one category of this classification, and enjoying that they are repeating the history. Thank you.
Since I showed this summary slide, I'd like to continue this discussion on the different optimization schemes. So in particular, there was this stochastic search that we didn't discuss too much, but Anders probably is not here. But anyway, that was his paper on the variational Monte-Carlo optimization of MPS, right?
Yeah.
If I remember correctly.
Yeah.
In my experience or expectation, I wouldn't expect those stochastic optimization scheme to scale up really to a large dimension of the variational parameters. That's my experience. Another thing is that in variational Monte-Carlo application, they have to deal with stochastic because they need to sample from Monte-Carlo procedure, right, to estimate the gradient. So then, but in many of the tensor network calculations, we got the gradient information deterministic. I think that's a plus. While in machine learning, typically people also do stochastic optimization. That's because the data set was still so huge, and in each of the optimization step, they cannot afford to go through the whole data set. Therefore, they do mini batch. Therefore, they get stochastic gradient.
Yeah, in that case, the data itself is stochastic.
Yeah, and but the other point is that in machine learning, typically people do not really care too much about reaching global minimum. In the end, they care about, for example, the ability to generalize. They call it generalization ability. Therefore, there are many discussions that some of the stochastic gradient design sometimes help you to reach a wide but shallow minimum that is good for generalization. While in many of the ground state calculations, they care about, to my understanding, the deterministic gradient is still the way to go.
Yeah. So in the case of machine learning, sometimes local minimum is agreeable.
Yeah, it's acceptable. But then it still depends. So whether it's a deep and very narrow minimum, or whether it's like shallow the wide minimum, they prefer to get those wide shallow minimum because in the end they calculate the performance on the test set on the sync data, and very often those stochastic fluctuation in the gradient help you to reach this wide minimum. So that's why there are many discussions about the generalization ability of different optimizers.
Yeah. So this kind of discussion might become important when we apply the tensor network to the machine learning. I might not ask you whether your wife is a local minimum or global minimum from the candidates. I'm joking.
I have a question. As you mentioned, for a finite bound dimension in this tensor network state, at the critical point, the correlation length is always finite.
Almost always.
Almost always. Does it mean the critical exponent is a mean field critical exponents or not?
Okay. This depends on a way of estimating the critical exponent. So at the very vicinity of the transition point, you encounter funny behavior because the TPS always two-dimensional, but the real system is three-dimensional. But some step away from the critical real vicinity of the transition point, you get correct answer. So just estimating the critical exponent from those data, somewhere around the transition point.
So you mean you can get the critical exponents which deviates from mean field values?
Yeah, it can be deviate. So, for example, DMRG shares the same problem with this approach, tensor product approach. So, if you perform the DMRG very carefully, then you find out that at the transition point, DMRG deduces funny data. But normally people do not care about that because this is only the width of machine epsilon. So every time they use the energy to detect the critical exponent, they just gather data some point around the transition temperature. So that's sufficient.
Because in DMRG calculation, you always deal with a finite system. So for finite system, you have a critical point.
In the case you use the finite system, you're right. In the case they use the infinite system, and it is possible to perform the scaling with respect to chi. Anyway, some sort of finite size scaling or finite classic scaling is necessary, and the case is the same for the three-dimensional case, and finite or finite size scaling is necessary for the estimation of critical exponent for a given system.
On this is Anders had another paper related to this topic, right? They did a very accurate calculation, I guess, for MPS using high precision numbers and seeing whether it should mean field behavior. To my understanding, if you really zoom in very closely to the transient point, you'll always see mean field like behavior.
Yeah,
this is like crossover. If you it's crossover from the non-mean field behavior to the mean field.
Yeah.
Right? Maybe we need that.
I know that point. Yeah, so you are right. You are very correct. And that transition behavior was once studied by Baxter and in the age of 1970s. So here, again, the history repeats.
I think we can also understand it this way, because in field solution is generally a product state.
Yeah,
Of course, not in the real space, but in some
it's also.
kind of representation.
Yeah.
So if you keep doing that, for example, construct a tensor narrow space in that representation, then any kind of tensor narrow space with bound dimension more than 2, or 2, more than 1, should go beyond this debate from the field solution.
Far apart the transfer point in reality.
Of course, in real space, the question we just discussed is, in real space, with the final bound dimension, give you the right critical degree, which is not revealed. I think the answer is yes. Otherwise, you will always get a wrong answer for exponent. But actually, from the emerging calculation or any other kind of calculation, we were always from that the exponent. There's some errors, but not very far from the very important from other kind of calculations.
Anyway, it is important to collect reliable data for sufficiently large kind.
All right, thank you again.